Chapter number 6 is going to start talking about the periodic table. And what we're going to do is we're going to look at a little bit of the history behind that periodic table and where specifically it was developed. In this chapter, like I said, what we're going to specifically look at is that periodic table. And we're going to talk about some trends, some things that you see over and over on the periodic table. One of the early classifications of the periodic table came from Johann Doberiner, and he was a German chemist, but the thing about his is it really wasn't a periodic table, but more than anything it was taking the elements that they knew of at the time and finding a way to find some characteristics that were in common with them. In 1817, what he did was he found that the properties of the metals calcium, barium, and strontium were very similar to one another. All three of these elements are going to be somewhat reactive with water. All three of them are going to be a shiny silvery metal. All of them are going to be very malleable, meaning that they have a soft characteristic to them. The other thing that he noted was the atomic mass of strontium was about halfway between calcium and barium. Now when you look at the periodic table, you're going to notice calcium is on top, you're going to notice barium is on the bottom, and strontium was in the middle. Well, again, what he said was, if I take the mass of calcium, add it to the mass of barium, and divide it by 2 to figure out what that average was, it was pretty close to exactly what strontium was. What he did was he called these elements triads. It is a group of 3 elements with similar properties, and also where that middle element has a mass that is halfway in between the first element and the third one of that triad. So the example that I just got done talking about, calcium. Okay, calcium has a mass of 40.1. You look at the last one, barium, 137.3. If I add both of those up and divide by 2, I get about 88.7. And when we compare that to strontium, strontium's real mass is about 87.6. Again, what we're saying is with a triad, what we're looking at here is, he said, okay, we're going to look at 3 elements that are in a column. He said, okay, calcium is here. He said barium is here. And again, if I add up the first and the third and I divide by 2 and figure out what that average is, that should have been pretty darn close to what strontium was. And again, when we compare it, it was very close. Do triads exist today? No, but there are portions on the periodic table where it does exist. But again, this was one of the earliest classifications for the periodic table, okay, or classifying the elements of the current periodic table. In order for something to be a triad, I say that it has to be within 2 units of what that average is. So where this one was 88.7, I would have gone all the way down to 86.7. I would have gone all the way up to 90.7. So within 2 units of it in order for it to be classified as a triad. The second attempt at classifying the elements that we currently knew of was by John Newlands. John Newlands was an English chemist, and he came around and was looking at the elements at around the time 1863. And again, what he did was he looked at their atomic masses. And he said, okay, for the elements that we know of at our time, what I'm going to do is I'm going to place the lightest element first. I'm going to place the heaviest element last. And I'm going to start organizing them by increasing atomic mass. And the thing is, when he looked at the elements, he noted that there was a similar or a repetition of the properties every 8th element. So for example, if you look at element number 1 and you look at some of the characteristics of it, both chemical and physical, we go to element 2, 3, 4, and again, once we got to that 8th element, he found out that the properties of it were very similar to element number 1. And what he did was he called this the law of octaves. So again, he started going and said, okay, we're going to put 7 groups, okay, or 7 vertical columns going along the periodic table. So he went ahead and he started with lithium, beryllium, boron, again, lightest, going over to heaviest in the row. And all of a sudden, once that 8th element, sodium, came around, again, it had very similar properties to lithium and sodium. Boron and aluminum had characteristics that were similar. Fluorine and chlorine had characteristics that were similar. And again, what he did was he did this for all of the elements that he knew of. Again, I only put 15 up here, but again, I wanted to show you that his periodic table would have went by 7 groups, and then all of a sudden it repeats row number 2. Go 7 more elements, and then we're going to start row number 3. And again, going from lightest down to, well, in this case, the heaviest being potassium for the example that I have. But again, he went from lightest to heaviest and noted that there was a repetition every eighth element, and that repetition every eighth element he called the law of octaves, which is the same properties. And again, when I use the word properties, I'm meaning both physical and chemical, but the same properties appear every eighth element when the elements are listed in order of their atomic mass, or in order of their increasing atomic masses. Again, these were some of the early attempts. The periodic table really got rolling when Dmitri Mendeleev came around. Dmitri Mendeleev, he was a Russian chemist, but he is basically classified or given the name father of the periodic table. He is the first scientist to give us something that basically resembled exactly what we have today. Was he 100% correct? No, but you're going to see why he was given that title of father of the periodic table, because of some of the stuff that he did with his periodic table. He also was an individual that said that, again, they're going to be functions of their atomic masses, meaning that we're going to go ahead and place the lightest one first, and we're going to place the heaviest one last. Mendeleev believed, though, that these physical and chemical properties occurred after periods, which are horizontal rows that could vary in length. Now, again, when you go back to Newlands, remember, he said we would have gone 7 across and then went to row number 2, went 7 across, went to row number 3, went 7 across, and so forth. But the thing about Mendeleev is, if you look at him, he said that those horizontal rows could vary in length. If you look at our periodic table, again, that first row only has hydrogen and helium in it. So again, that row is only 2 elements long. Now, if you look at rows 2 and 3, that's going to be 8 elements in length. So again, it could vary in length. Again, we're going to talk about that importance in just a little bit. But the thing is about Mendeleev's periodic table that made it so unique was, if there was something missing, he went ahead and made predictions about it. He didn't just say, okay, we have 50 elements, let's just place all 50 of them, and we're going to place them in order. Well, the thing is, if Mendeleev noted, again, what masses were, he looked at what Doberiner talked about with triads, and he said, okay, again, if there should be a 30 difference, okay, there's going to be an element that goes here. But if all of a sudden he noted that there was, say, an 80 difference, he put a blank spot there and said, you know what? We're missing an element. This is an element that we have not found yet, but it is going to be discovered. Well, that's what he did. For example, the first element that he did was ecosilicon. Eca just means Latin for coming after. So what he said was, there is an element that is going to be below silicon, and we're going to call it ecosilicon. Now, he didn't just say that it's going to be an unknown element. He went through and he made predictions about it. He said it's going to have an atomic mass of about 72. He said it's going to have a high melting point. Now, how high, I'm not sure exactly. I'm sure he would have compared it to the elements around it, but again, it's going to be a high melting point. He said it's going to have a density of about 5.5. He said it's going to be a dark grayish metal. And he went ahead and he looked at a chemical property also, saying that if it goes ahead and combines with oxygen, we're going to need one of the ecosilicons, and it's going to react with 2 of the oxygen particles to give us what would be a formula of ESO2. Now, Mendeleev dies. Okay, he never actually sees this element found. But many years later, the element was actually found, and that element was germanium. Its atomic mass was 72.61. Remember, Mendeleev said it would have been 72. Pretty close. He said high melting point. Well, the actual melting point is 945 degrees Celsius. He said it would have had a density of about 5.5, when in reality it's 5.323. He said it was going to be a dark gray metal. It was indeed a grayish metal. And again, he said ESO2, well, when germanium reacts with oxygen, it forms GeO2, again in that 1:2 ratio. Now, Mendeleev did this all across his periodic table. He didn't just do it for a couple of elements. He went through and said, again, here's the elements and this is where they go. These are the blank spots, and these are all of the missing elements that we know of. And here's the properties. When we find them, this is what they are going to look like. On the periodic table, that word periodic just means a repeating pattern. The best repeating pattern that we know of is a calendar. You start at Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and guess what? We're back to Monday again. And he went ahead and he called this the periodic law. And he said that the properties of the elements are a periodic function of their increasing atomic masses. Again, when I say that word properties, I mean both physical and chemical. So again, repeating it, the chemical and physical properties of the elements are a periodic function of their atomic masses. Henry Mosley, like I said, Dmitri Mendeleev was father of the periodic table, but again, it was with the current information that he knew of. Henry Mosley was able to, again, when you go all the way back to Thomson and the discovery of those protons and electrons and neutrons and things like that, Henry Mosley was the individual that did an X-ray experiment and found that there was an integral positive charge in that nucleus, and now we call that thing the atomic number. Using that X-ray experiment, again, there was that integral positive charge that we call the atomic number, and what he said is we're going to arrange the periodic table according to atomic number. Again, if you go back and look at how Mendeleev would have done it, he was probably about 90-95% correct, but there were a few of the elements that were going to be off in order that would actually have to be switched around. For example, potassium is one that if you go ahead and look at potassium, it is going to be in that first column, but again, if you look at its atomic mass, it should actually flip places with argon. And again, if you remember some things about the periodic table, that first column on the periodic table is very, if you remember some things about the periodic table, that first column is going to be very reactive with water. Argon is actually in with the noble gases, that very outside column, meaning that they are unreactive. By Mendeleev's organization, we would have had an unreactive gas, argon, in group number 1, saying that it should have been reactive, meaning also that potassium, which is very reactive, should have been where argon was, meaning that it is an unreactive gas, and we know that's not true. So what he did was he reorganized the periodic table, fixing a few of Mendeleev's mess-ups, or again, I guess with the technology that he knew of, some discrepancies with it, and again organized his by atomic number. He had to restate Mendeleev's periodic law, and now he called his the modern periodic law, which just states that the physical and chemical properties of the elements are a periodic function of their increasing atomic numbers.